Covariant derivatives from my book, Tensor Calculus and the Theory of Relativity. In a flat Euclidean space, moving a vector from one point to another in Cartesian coordinate doesn't change its components. Its magnitude and direction are preserved, meaning that the vectors remain in parallel under parallel transportation. Thus, the derivative of the vector component is zero. But when it comes to curvatures, moving a vector straight relative to the surface changes its direction with respect to the fixed coordinates. The vector components are changed. We can capture the curvature when the direction of the vectors changes when transported around a closed loop in curved space. This method is called holonomy. Thus, calculus and Euclidean geometry are no longer applicable. The big question is, how do we take a derivative when the basis vectors themselves are changing? Here comes the significant role of covariant derivatives. Think of them as a correction for the derivatives that account for the curvature by adding the Christoffel symbol. Again, covariant derivatives allow us to differentiate vectors in curved spaces by tracking the change as we move through the curved space-time. This equation is written in Einstein's notation so that the indices can take values such as 0 for temporal component and 1, 2, and 3 for spatial component. The first part is the ordinary derivative, where the index v indicates the direction of motion through space-time with respect to a chosen coordinate direction depending on the value taken 0 or 1. The vector v mu1 represents the components of a vector field. Could be a momentum vector or an electromagnetic field in curved space-time. And the index mu1 represents the component of the vector being analyzed, which could be 0 or 1, identifying how the vector behaves in different directions of space-time. Jumping on the second part of the equation, we have the ordinary partial derivatives. This term indicates the change in the vector components changes with respect to the coordinate direction without considering curvature. But the magical green part is the correction term that accounts for the curvature of the space. It adjusts the rate of change of the component vector based on how the basis vectors change. The Christoffel symbol modifies the standard derivative to account for how basis vectors change due to curvature. And the vector sigma highlights specific components of the vector being transported through curved space-time. However, the math beyond Christoffel arises from the metric tensor, which encodes the curvature of space-time. It describes how length and angles are measured in the curved space. For example, the metric tensor is expressed in spherical coordinates, showing how distances are wrapped as this equation. Unlike the flat surface, which used to be equal to the Kronecker delta or the identity matrix. Thus, the Christoffel symbol is equal to this, where the inverse of the metric tensor is used to raise indices, allowing us to relate covariant and contravariant components. And the partial derivatives show how the components of the metric tensor change in different directions. Thus, the space curvature affects the vectors. We can also describe the shortest curved path. Unlike the flat Euclidean space where the straight line is the shortest path between 2 points, the geodesic is the shortest path between 2 points in a curved space-time manifold. This is why general relativity describes gravity as a manifestation in space-time curvature rather than a force. The geodesic is expressed by this equation, whereby the second derivatives ensure that there is no acceleration along space-time curvature. In other words, it is the shortest and straightest possible line in a curved path. X mu1 is the coordinates of the geodesic as a function of an affine parameter tau. The affine parameter tau is the proper time for massive particles or an arbitrary parameter for massless particles like photons. It allows us to describe how the coordinates change along the geodesic. Summing up all that, covariant derivatives is an extension of the derivatives to be applicable on Riemann spacetime curvatures by adding the Christoffel symbol, which accounts for the change in the basis vectors.